Welcome to another video in the graph series. Today we are going to look at the same question that we saw in the last two videos, but we could not pass all the test cases in the last two videos. Why? Because we were using adjacency matrix to represent the graph, and there were a lot of faults or there were a lot of zeros in the adjacency matrix. Basically, we ended up using a lot of space that we do not need. We can optimize that using adjacency list, and that is what we are going to try doing today. We are going to use adjacency list to represent our graph, and then we are going to use DFS to solve our question today and BFS in the next video. Before we move ahead, I would just like to take a moment to remind you to be consistent and make sure you do not miss any videos in the graph series. So make sure you subscribe, hit the notification bell icon. You will also stay motivated, and you have no idea how much your support will mean to me. There's so much of free content available on the channel. There's HLD, LLD, DSA, Advanced C++, tutorials, mock interviews, and so much more. So if you think I deserve your support, please subscribe, hit the notification bell icon. And there's obviously a bunch of stuff that I cannot do on YouTube, like mock interviews, live interactive classes. So we have educourses.com. We have live courses, self-paced courses with live doubt solving support, which both of them we have mock interviews, and we have a lot planned in LLD, HLD, Advanced C++, DSA, and so much more. You have no idea. So if you want me to be part of your further learning journey process, please check it out. The link is in the description. And now let's continue. So in this, let's do a quick revision and let's look at the question that is given to us. So here you can see two examples. We have to see if there is a path from the source to the destination. So here we are given the number of vertices and we are given some edges. We have to form a graph, and then we have to see if there is a path from source to destination. Here you can see there's a direct path from source to 2. There's one more path. But over here, there is no path from 0 to 5. Why? Because this is disconnected over here. So first thing first, let's see how we can represent this graph using adjacency list, and then we will try doing the DFS. I've made both the graphs that are given in the examples over here. Let's see how we can visualize them in the adjacency list. What do we do in adjacency list? First, we write down all the nodes. So 0, 1, 2. And then we see who are the neighbors. So for 0, who are the neighbors? The neighbors are 1 and 2. For 1, who are the neighbors? The neighbors are 0 and 2. For 2, who are the neighbors? 0 and 1. Similarly, over here, let's see. So here we have to write all of the numbers 0, 1, 2, 3, 4, 5. So that is all the nodes that are there. For 0, who all are connected? 1 and 2. For 1, who all are connected? Only 0. For 2, who is connected? Only 0. For 3, who is connected? 4 and 5. For 4, who is connected? 3 and 5. For 5, who is connected? 3 and 4. So this is how our adjacency list is going to look like. Usually to represent adjacency list, what you can use is a map. Like for a map, so this is going to be a key. So the number is going to be the key. And then there is going to be a list, right? That who are the nodes that are connected from this particular node. From 0, who are the nodes that are connected? From 1, who are the nodes that are connected? Over here it is 2, 2, but you can see that there can be 0 elements, there can be 5 elements, there can be 10 elements, like that, right? But in this case, in the example that is given to us, in the question that is given to us, we do not need a map actually. We can take a map and we can represent like this also, but there is one more better way, and I wanted to actually think about this better way, and I wanted to think that why we can use this particular method, because this map wala method we will use in a lot of questions. This is particular to the questions like this. So here if you think about it, we are given n nodes, right? And each node is represented by an integer which is from 0 to n minus 1, correct? Here there are 3 nodes, so 0, 1, 2. Here there are 6 nodes, so 0, 1, 2, 3, 4, 5. So we know that all the nodes, so basically all the keys are going to be 0 to n minus 1 only. So why take map and why store the keys? Why can't we just keep an array of arrays? So let me show you over here, what do I mean? So here what I mean is that instead of keeping a map like this, why can't I have an array? So the number of rows in this 2D array is going to be n, but the number of columns is going to be variable. So in this example, it is like 1, 2, 0, 2 and 0, 1. But if you think of this example, we are going to take one array, okay? And then in each element in this array, there can be any number of nodes. Like here, there can be 1, 2, there can be 0, there's 4, 5, there is 3, 5, and then there is 3, 4. Correct? Like this, there could have been even 6, 7 in one particular array. So you get my point, because whenever I want to access this array, I can just take this entire thing, suppose this is called graph, and I can go like graph of 0, 1, 2, graph of 2, right? Why am I saying this? I hope you are able to think about it. Because the keys itself are like from 0 to n minus 1. So I do not need to explicitly store the key. I can actually use the index of that 2D array itself, and I can represent adjacency list in a very simple way. So I just wanted you to notice this thing, but let's continue representing the graph with the usual adjacency list at how it looks, so that you are used to writing it in the map and you are able to tackle all kinds of questions. So let's see how the adjacency list is going to look like. Again, let me repeat it for you. We are going to write 0, 1, 2. Now 0 is connected to 1 and 2, 1 is connected to 0 and 2, and 2 is connected to 0, 1. Here again 0, 1, 2, 3, 4, 5. Here 0 is connected to 1 and 2, 1 is connected to only 0, 2 is connected to only 0, 3 is connected to 4 and 5, 4 is connected to 3 and 5, and 5 is connected to 3 and 4. So these are the neighbors. Now the DFS is actually very same to adjacency matrix. The only difference is whenever we have to find the neighbors for a particular node, like for example, I have to find the neighbors for this guy, I just have to go through this list. When I have to find the neighbors for this guy, I just have to go through this list. Instead of going through the entire row in the adjacency matrix and seeing whether it is true or false, over here I just need to go through the list and see that okay, these are the neighbors, and I will see have they been visited or not. Since we have already done the dry run in the last video, we will do it quickly this time. So here again I am going to be using the stack. In our code we will be using the recursive stack, and I am going to take the array visited. So here there are 3 nodes, so 0, 1, 2, initially marking all of them as false, not visited. I am going to start from my source node, which is 0. I am going to put it in the stack and mark it as visited. Who are the neighbors of 0? They are 1 and 2, but we are going to go one by one. So we first go to 1 and mark it as visited. So I marked this as visited and I go to 1. Then I go to the neighbors of 1. 0 is already visited. 2 is the other neighbor. I push 2 and I mark it as visited. Who are the neighbors of 2? The neighbors of 2 are 0 and 1. They are already visited, and so we are not going to push anything, and we are done with 2. So we are going to pop it out, and we are going to pop this out. We are going to pop this out. But the moment we would have found 2, we know that we have found our destination and we can just return true. Similarly over here, let's take a stack and let's take the visited array. So it is 0, 1, 2, 3, 4, 5, initializing the entire thing with false. So false, 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 false. I am starting with 0. Who are the neighbors of 0? The neighbors of 0 are 1. Let's start with 1. We push 1, we mark it as visited. Who are the neighbors of 1? It is 0, but like for neighbors of 1 it is 0, but it is already visited, so I am not going to do anything. I am going to pop it. It is also not our destination. Then I am going to come to the second neighbor, which is this, so which is 2. I am going to put 2 and I am going to mark it as visited. All the neighbors of 2 are visited, so I am not going to do anything. I am going to pop it. Done with all the neighbors of 0, I am going to pop it. Now I did not visit 5 at any moment, which was my destination, so I am just going to return false. Very easy. Let's try writing the code. I'm going to be first writing the code in C++. For Java people, you can go to this time. Yes, we are given the n and the edges, so we are first supposed to form the graph. So how is our graph going to look like? It is going to be an unordered map. And what is our key? Our key is an integer. And what is our basically the value? The value is a vector, right? So vector of what? Again, vector of integers. And I'm going to call it graph itself. Now I'm going to fill this graph. For that, I'm going to go through all the edges one by one. So for auto edge and edges, again, there are 2 things in the edges. So there is one u and then there is v. I'm going to take out all of that. So edge of 0 is u and edge of 1 is v, right? I don't need it, but I'm keeping it for simplicity. Okay, now I need to add this to our map. How can I do that? So in graph of u, so basically that is my key. What am I going to do? I am going to push back my v. So basically when u is the key, I am pushing v, and similarly when v is the key, I am pushing u. Why am I doing that? Because this is bidirectional. Remember these details, right? So we have formed a graph now. So now before doing DFS, what else do we need? We are dealing with graphs. So for graphs, what do we need? We need a visited array. How big is our visited array going to be? Number of vertices or number of nodes, which is in this case n. So I am going to keep another vector. It can be a boolean itself. I am going to call it visited. Size is n, initializing the entire thing with false. And now we are going to write a recursive function which we can call anything. We can call it helper, we can call it valid path helper. I am going to call it DFS to keep it very clear. And that is the one that is going to return as the answer boolean itself. So I am just going to return the answer from here. What all things do I need to pass? I definitely need to pass the graph. I need to pass the source that is given to us, the destination that is given to us, and the value n. I also need to pass the visited array. Let's try writing this function. So I am supposed to be returning the answer and then DFS. So I have to pass this graph, right? In C++, remember we have to pass everything by reference. Very good. So we are passing by reference. And what else do we need to pass? The source, the destination, and then the visited. So vector of bool and visited and n, correct? So in this DFS function, if we ever find the answer, we are going to return true. Otherwise, in the end, we are going to return false. Now, what is the main thing that we have to do in DFS? We have to go through all the neighbors. Now, the only difference between adjacency matrix and adjacency list is that in adjacency matrix, in order to go through all the neighbors, we have to go through the entire row of the matrix. Here, we don't have to do that because in the list, we have added only the edges. Other nodes are not added only. So that is better for us, right? That is the more optimized solution. So how will I go through all the neighbors? I just have to write a simple for loop that for every neighbor in this graph of source. So basically in this graph of source, every single element that is there in this map, in this list. So basically source is the key. There is a list for every value in that list that is a neighbor. Now I just need to check one more thing. What is that thing? That it is not visited. So I just need to make sure that my neighbor is not visited. And what if it is not visited, what am I going to do? I am going to call the DFS again. I am going to pass the graph, but now my source will become what? My source will become my neighbor. Destination will remain same, visited will remain same, n will be there, and that is it. Now this will also check if this returns true at any point. What am I supposed to do? I am supposed to return true because I found a path, right? If I find a path, I will return true. Otherwise, in the end, I am going to return false. So here I am checking if it is visited or not. But in the starting, I obviously also need to mark it as visited. This is very, very important. And at every point, I can just check that if my source is equal to my destination, I can just return true from here itself. And that is it. We are done with the code. And if you are getting confused with this auto, you can actually write it as integer because every neighbor is the integer over here. Let's try running it. And it ran. Let's submit it and see. So we have finally passed all the test cases. Unlike when we used adjacency matrix, here we use adjacency list and we were able to pass all the test cases. So yes, let's discuss the time and the space complexity now. Starting with the space complexity, how much space do we need to store the adjacency list? Now, how many nodes are there? There are order of V, right? So in the map, how many keys are going to be there? They are going to be V keys. And now for total number of V keys, what will be the number of connections? It will be E because E are the total number of edges. In this case, because it is bidirectional, it will be 2E, right? Because E edges are given, but it is actually bidirectional. So think of it like for every edge, U is also connected to V, V is also connected to U. So there are two edges, right? So the space that you're going to take is, let me just write it down like this, order of V plus 2E, correct? And now what other space are you taking? You are taking the space for visited array, that is how much? That is order of V. And then you are taking another order of V for what? For recursive stack. Again, in the recursive stack, what is the maximum space that you are going to take? In the worst case, all the nodes are going to be there in your recursive stack. So this is going to be order of V. So this is for the graph, this is for the visited array, and this is for the recursive stack. So this is the space complexity. Again, for time complexity, for DFS, you can think in very simple terms. Through the entire graph, you will be visiting the node exactly once. Once it is visited, you are not going to be visited again. So in the worst case, it is going to be order of V plus 2E only. It is going to be true for PFS also. So for both PFS and DFS, when you are using adjacency list, for the algorithmic part, your time complexity and your space complexity is going to be order of V plus 2E. 2E is because it is a bidirectional graph. If it was a unidirectional graph or a directional graph, it would be just order of V plus E. Coming to the Java code, again we are given n edges. We are supposed to form the graph. How is our graph going to look like? It is going to be a map. So what is the key? The key is an integer. And corresponding to each key, what do we have? We have a list of integer, correct? So we have a list of integers and I'm going to call it graph itself, and this is nothing but a hash map. Now we need to fill this graph, and how are we going to go do that? We are going to go through all the edges. So for every edge in this edges, what am I going to do? Now in every edge there are two values. There is u, which is edge of 0, and there is v, which is edge of 1, correct? Now what do I need to do? I need to find the key u, and in that list I need to add v. Similarly, I need to find the key v, and in that list I need to add u, correct? So let's do that. In graph, what we are going to do? We are going to compute if absent, and in u, what am I going to do? In this value, I am going to do new array list. So for this u, there is an array list. In that we need to do what? We need to add v, correct? And similarly, we need to do the same thing, that when key is v, in that array list we need to add u. So we have filled our adjacency list now. Now what do we need to do? We need to do the DFS. Because we are dealing with graph, what else do we need? We also need a visited array. The size of the visited array will be what? It will be n itself. So boolean visited equal to new boolean, and the size of it is going to be n. Now we can call our recursive function, which we can call as helper or valid path helper, or what do you want to call it. I am going to call it DFS, and I am going to return the answer from there itself. I am going to pass my graph, I am going to pass the source, the destination, the visited array, and the n. And let's try writing this function. So here I am going to do private boolean and DFS. What all things am I passing? I am passing the graph. This is my graph. I am passing the source, the destination, the visited array, and I am passing n. So in this function, I am going to be returning boolean. If at any point I find my destination, I am going to return true. Otherwise, in the end, I am going to be returning false. In DFS, what is the main thing we are supposed to do? We are supposed to go through the neighbors, right? The only difference between adjacency matrix and adjacency list is that in the matrix, we had to go through the entire row and see, is it neighbor or not, is it neighbor or not, is it neighbor or not. Versus in adjacency list, we have added only the neighbors, we have added only the edges. So every value in the list for a particular key is going to be its neighbor. So it's going to be very easy to iterate. So for every neighbor, so basically you go through whatever I in this graph. So how do you get the list corresponding to a particular source or a particular key? You're going to do graph.get source. So for this entire list, okay, every single value that is there is going to be a neighbor. You do not need to check. It is a neighbor for sure because it says adjacency list, right? But before calling the DFS function again on that neighbor, before moving to the next sub problem, what do we need to check? We need to check that this neighbor has not been visited already. We need to make sure that we are not stuck in a forever loop, or we are not visiting the same nodes again and again. So if it is not visited, only then what I will be doing is I will be calling the DFS function again. I will pass the graph, but now my source is going to become my neighbor. This is my new sub problem. I am doing recursion. Destination is going to remain same, visited is going to remain same, n is going to remain same. And if this returns true, if it returns true, that means I have found a path and I can just return true from here itself. When we are dealing with visited, two main things. First, we need to check whether it is visited or not. Also, we need to mark it as visited. When do we mark it as visited? Before we start going through the neighbors. So visited of source is true, and also we need to add a check that if my source at any point, if it becomes equal to my destination, then I can just return true. You can call your source as current. So here you would be dealing with, if my current is equal to destination, then you can return true. If visited of current is true, so you will know that you're dealing with a current sub problem or a smaller problem. Let's try running it. So this works. Let's submit it and see. So yes, we have passed all the test cases. Unlike the cases when we use adjacency matrix for both BFS and DFS, we were able to pass all the test cases. Let's quickly look at the time and the space complexity as well. What will be the space complexity? Here for the adjacency list, what is the space that we need? Now what will be the number of keys? The number of keys is what? It is V, correct? That is the number of keys. Now, what are the number of connections that we do in total? That is E, correct? But in this case, it is actually 2E. Why? Because here there is bidirectional graph. So for every edge U to V, you have to make a connection from U to V also and from V to E also. So your edges actually become twice because it is bidirectional. So in the graph, you are adding for both of them, right? So your adjacency list takes how much space? Order of V plus 2E. Other than this adjacency list, where else are we using space? We are also having the visited array, which is another order of V, and there is also your recursive stack. Now recursive stack, in the worst case, how big is it going to be? Order of V. Why order of V? Just imagine in the worst case, all the nodes are going to be there in the recursive stack, right? They cannot be more than that because you would have popped them out. And the main thing is that you are not visiting any node again, you are maintaining a visited array. That is why this is the space complexity for the visited array, this is the space complexity for the recursive stack, and this is the space complexity for your adjacency list. Now, what is the time complexity? For DFS, you can think of it in simple terms. You will be visiting each and every node exactly once. And how will you do that? Order of V plus 2E. So that is the time and the space complexity that you need for both BFS and DFS actually when you use adjacency list. We will be solving the same question using BFS and adjacency list in the next video, and that will be the final video of this question, and I hope you are enjoying the series. I'm putting a lot of effort in this. I'm writing the code in both C++ and Java, and I hope you're enjoying it. And if you have any doubts, let me know in the comments. I'm here to help you out. I hope you can put in the effort to subscribe and hit the notification bell icon so that you do not miss any videos and you stay with me till the end of the series. I hope we all can motivate each other, and do check it out, 𝐸𝐸 if you're looking for live courses, interactive courses, and if you're looking for live doubt solving sessions, you can sign up on 𝐸𝐸. The testimonials, the week-wise curriculum, everything is mentioned over there, and I hope to be part of your learning journey. See you next time.